My name is Julia Pastis, and I am a member of the Santa Rosa High School Shell Eco Marathon team. And in this video, we will be showing you where we are on various different aspects of the car. So, in order to give you an overview of what we're going to cover in the video, we have a timeline, also to let you know when we expect to have these aspects of the car finished. So the chassis we expect to have finished by the end of December. We already have our process and our design, and we're close to getting our supplies. So it should be done by the end of December, so that over winter break, we should be able to finish the fiberglass body. We already have a scale model and we have our process perfected, so we should be able to have that done by the first week of January. From there, we expect to finish our motor controller by the end of January. We have a good start on that, and for our brush version, we expect that to be done quickly. We also are working on an ongoing brushless solution, which might take longer because it's more complex, but we'll see if we can also work on that. But as our solution that we know will work, we have our brush solution. So then in February, we expect to install these aspects that we will have finished by then. We will install the electronics. We will also install the seat, the wheels, the pedals, all of the things that are essential for the driver. And that leaves the month of March for us to test our design and make it as good as possible for the competition on April 3rd. In addition, we can use the month of March to deal with any problems that may arise between now and then. So now we will go through each of these aspects more in depth. Thank you so much.
My name is Christina Garcia, and I am part of Santa Rosa High School's Science Club, which is taking part in the Shell Eco Marathon. This is our box diagram of how power will flow through our car. It begins with the 48-volt battery with battery management system and charger, which looks like this. This is going to be connected to our external shutdown switch and our internal shutdown switch, which both look like this. That's all connected to our 48 to 12 volt DC to DC converter, which looks like that. It has to be 48 to 12 volt because our motor controller can't handle 48 volts, it can only handle 12. We are going to include a NO 30 amp relay and an NO deadman switch. That's our relay, and this is our deadman switch. We're going to use two of these switches, one for the deadman switch and one for the horn, which is going to look kind of like this. Power is going to flow to the motor, which will look like this. It's our 48 volt brushless DC motor. Assets of the car include a rack and pinion with a ball and socket, which help steer the car, a 5-point harness seatbelt thing for the driver, of course, and last but not least, the butterfly steering wheel.
This is our breadboard. Ignore the fact that there's an Arduino board there. It serves as no functionality in this circuit. So this is our engine, and it's turning. And the potentiometer can speed it up or slow it down by telling the NE555, which is here, what to do, basically. And the pulses, right here, changes as I speed the motor up and slow it down. So this is the duty cycle. This represents the off time of the circuit, and this represents the on time of the circuit. As I turn the potentiometer up to increase the speed of the motor, you can see that the duty cycle changes. The off time decreases and the on time increases, allowing more energy to enter the motor and speed it. So when the energy increases, the motor speeds up. Our select motor needs 48 volts to power, and it will draw 25 amps. In order to power that motor, we will have to change a few components on our breadboard, mainly the transistor, which will be replaced by this one. To give us some leeway, it will take 75 volts and 80 amps. To safely handle 48 volts, we would also have to replace this diode with this diode. This is the one we've selected so far. It can take 100 volts and 150 amps.
Although we understand that an efficient brushless motor could achieve higher efficiency, creating a motor control for a brushless motor is significantly harder because of the necessity to create a varied duty cycle for not only one PWM wave, but for 3. Nevertheless, we currently have a prototype motor control that can spin a brushless motor. However, because our timing of our PWM waves is not quite in sync with our motor, our brushless motor is very inefficient. It requires a lot of power output from the power source to turn the motor. Even if we fix this timing problem, we would still have ways to go before we can apply our motor controller to the car motor. First, instead of being driven by 12 volts, the car motor will have to be driven by a 48-volt battery. This means we won't be able to use the same voltage for both the ICs and the motor. The ICs can still continue to run on 12 volts, but the motor will have to run on a power source of 48 volts. We can achieve this by having a step-down converter step down the voltage from 48 volts to 12 volts for the IC, while the motor runs straight from the battery at 48 volts. Additionally, we'd have to change all the MOSFETs so they're suited for 48 volts. Overall, we have a lot of work ahead of us if we want to implement a brushless motor versus a brushed motor. And currently, our brushed motor solution is significantly more efficient than our brushless motor solution. But if we improve the timing of the PWM waves for our brushless motor solution, there is a possibility that we could use it instead of the brushed motor.
Hello, this is Jeremy from the Frame team. I'm going to be going over our plan so far. So right here, I've got a 1-to-1, roughly, scale model of the frame we're going to do. There's going to be our driver, Kayla, and the outline of her. And then I've designed the frame around that. We're going to be using 6061 1¼ by 1¼ 1/8-inch wall aluminum tube. I've got a guy who can weld it up really nice, so we're set on that. This is going to be a rough 3-dimensional drawing of it, just for some conceptual purposes. And then over here, we've got the shop drawings for fabrication, which I'm going to be doing with my welding buddy here. So this is the top view. We've got the back support for the back wheel. We got standoffs so we can actually be able to steer, not have the wheels run into the sides, you know, kind of important. And then there's also another side view, the same view as over here. And then we've got all the dimensions called out here, along with sides, angles, all that good stuff. And we've got the material called out right here, right side. And there we are. All right, we're back in the shop. Got all the plans laid out. Here we've got some sample of the aluminum welds my welder did. Stacking dimes, to say the least. And here's going to be the material that we're going to be doing. It's the 1¼ 1¼ 1/8-inch wall. And there's the welds on that. So we should be pretty set.
Our team was asked to prove a process to make a fiberglass body. So first we waxed a pan and then put fiberglass over it with epoxy resin and hardener and made this as a sturdy first try. And then we made a styrofoam quarter-size model of our car. And first we put mud over it, then we waxed it, then we did we put fiberglass and epoxy over it to show that we could have a quarter-size model and we could make an actual size model of our car. So
our car will have 2 bicycle wheels in the front and 1 wheel in the back. All wheels will be 26 inches and the back wheel will have 42 tooth sprockets. The front wheels will be mounted on using a Cannondale lefty hub, which will allow us to attach the wheels on only one side. This is a diagram of how our wheels will be attached. All wheels will have hydraulic disc brakes, and the back wheel will have a rim brake as a backup. All wheels will also have low friction tires for faster acceleration. These wheels will be fabricated in a couple of days, and we will be ready to mount the wheels once the frame is ready.